A good question. I like that. Yes, everything originates from the parent. You as a child originate from your parent. When we talk about these types of graphs, there are something called parent functions. And on page 301 in your book, I want you to open up your book to page 301. Do that. Because there on that page, you will see 4 graphs. And I want you to screenshot those 4 graphs and put them into your notes. Because what I'm going to do is explain each different type of parent function. Those are the parents. And then we're going to take those parents, the original, we're going to do some things to them and transform them into something else. Now, before I explain each of those parent functions, I want you to think about another example. How many of you have ever gone onto one of those car manufacturer websites where you can build a car and then it'll tell you a price at the end? How many of you have ever done that? Okay, good. How many of you know what we're talking about, though? Like, you pick your model and then you do all your upgrades and you add your stuff to it. The parent function is like the basic model before you do anything to it. It's like the bare bones, most basic kind of model of car. That's what a parent function is. It's in one particular position. It doesn't really have that many numbers associated with it. It's super basic. Then, when you do things to it, whether it's adding numbers, subtracting numbers, multiplying by it, adding, subtracting, and multiplying, or dividing, then that changes what the graph is going to look like. And so you have this original sort of function, the parent, and then changes happen to it, and you get this transformation. Okay, so that's the general idea concept. The first one that we need to look at is the constant function. And again, I'm going to go through them 2 at a time, but these are the pictures that I had you add to your notes. The constant function is simply this. F of x equal a constant, meaning you're going to get some kind of horizontal line. In this case, y equals 1 is the example they've put here. A couple things to keep in mind. The domain will always be all real numbers for a constant function. The range is just going to be whatever that constant is. In this case, the range is just 1. Y always equals 1. F of x always equals 1. So the range is just that. That's the simplest one. And we won't actually work with that one too much. It is a linear function, but it's a very specific kind of linear function. The second one we will work with a lot. This is the identity function, y equals x. Okay? Every linear equation starts off as this. We can take this and transform it in many different ways. Every linear function you've ever worked with has an origin of this. And then if you add to it, subtract from it, multiply by it, divide by it, you just get a different kind of linear function. Okay, the thing that's nice about identity functions and linear functions is that the domain and range are always both all real numbers. The only time this isn't true is if it happens to be a constant function. Okay? Otherwise, this is going to be true. So one of the transformations that you'll see is we'll change the position of this. We'll move it to the right or to the left or up or down. Its slope will change. It'll be more vertical or more flat. But everything starts with this and transforms from there. Okay? So those are the first 2. The second 2, the absolute value function, which we've been talking about. That was in 2.6 a lot. We talked about that. The absolute value function always looks like a v. So when you see the absolute value signs, you know you're going to have some kind of v. Now, because of what we did in 2.6, we know that it doesn't always start in this position. Sometimes it slides up or down or left or right, and it can even flip over and be an upside down v. But this is the original parent function of an absolute value. The domain is always going to be all reals. The range is going to be So we have when the v is facing up, we have a floor. So the range is going to be f of x greater than or equal to whatever the bottom of the floor is. Okay, in this case, it happens to be 0. So you know that when you see the absolute value signs, that when we're talking about the graph, it has to be in the shape of a v. It has to be. Okay, and then the last parent function that we talk about has similar domain and range as absolute value, but the shape is different. This is called a quadratic. We know it's a quadratic because x is squared. When you see that square up there, then you know it has to be a parabola. That's what the name of the shape is. This is a parabola. And so the domain is all real numbers. The range in this case greater than or equal to 0. Like I said, the range for a quadratic and for an absolute value function are similar in the fact that there will be a floor if it's facing up. There will be a ceiling if it's facing down. Okay, question?
So basically...
So what we're going to be doing in 2.7 is we're going to figure out what happens to the parent function when we add to it, subtract from it, multiply by it. Okay, change the sign. Because the numbers in the equation will give us insight into what the graph will look like. So it isn't necessary every time to create a table of values and plot the points like we were doing in 2.6 for absolute value. If you know how the numbers affect the parent function, then you should be able to have a really good idea what that graph should look like and where it should be. Because in your homework today, you don't necessarily have to create a table of values. You can draw me a sketch if you know where it's supposed to be. Okay, and that's what we're trying to get at with some of this. Now, we're going to talk about 3 kinds of transformations. The first one that we're going to talk about is called translation. It has nothing to do with language. A translation simply is when you take the parent function and slide it left or right or up or down. Okay? So it's going to be facing the same way. The shape is going to be the same. We're just putting it in a different place on the grid. Now, sometimes we can combine more than one translation together. We can slide things right and down. Okay? Sometimes we can slide them left and up, or left and down, or right and up. Okay? But the shape of the graph won't change. Just the position of it would. Like, for example, if I put you in a different seat in this room, okay, you'd all still be facing the same way. You would still have the same shape. You would just be in a different place. That's all a translation is. And in this definition, I use the word slide because sometimes these are known as slides instead of a translation. So those 2 words can be used interchangeably, a translation or a slide. Now I'm going to talk about some concepts in terms of how we figure out whether it's an up or down or a right or left. And the way that I've chosen to coin the phrase that determines the direction that it moves, I put it in parentheses because it takes a little while to get used to, and after we get through both, you'll be able to see, oh, that's the difference. I got it. So if it doesn't quite connect right away, just be patient. It will. Okay? So here's our first concept. A vertical or up or down slide occurs when a constant is added or subtracted, quote unquote, outside of an x term. And I'm going to give you some examples that'll help make that seem like an easier concept to understand when I say outside of the x. So here are 3 examples. These are all outside. Write them down and I'll explain what makes them outside, if it's not obvious to you. I feel like this one, this g of x, is the most obvious one. I've got the x isolated inside of the absolute value symbols. The -3 is outside. Okay? In the first one, f of x squared, the plus 7 is outside of the squaring. The squaring is happening only to the x. The plus 7 is outside of that. And the truth is, this last one could be considered outside or it could be considered inside. It'll still transform into the same place. But I've chosen to put this one in an outside position. Okay? So, there's two things that you're going to have to do in your homework. One, you're going to have to describe the transformation. And then two, you're going to have to graph it. Now, when I ask you to graph it, I do not need a table of values, exact points. What I need is a sketch that looks pretty close to the parent function, but you've put the transformation in the right place. So since these are all outside examples, that means there's going to be a vertical slide. Which way do you think the parent function will go for the very first one? Raise your hand if you think you know. Silly, what do you think? Up 7. That is correct. It will go up 7. Positive. We know it's a vertical slide because it's outside. Since it's plus 7, it's going to go up 7. Okay. Now, before we draw some of those, go ahead and find the next 3. You just write down and describe which direction those next 2 are going to be. I said next 3, but next 2. Okay, for the second one. Elise, what did you say for the second one?
Up 3.
Up 3.
Yeah. Because it's added or subtracted.
But it's subtracted.
But it's still added or subtracted. Oh, wait.
Subtraction. It's negative. Which do you want to fix it?
I lied.
What? Down. Because it's negative 3, it's going to go down 3. How many had down 3? Very good. Way to correct. All right, Elise, I'm going to give you a shot at redemption. How about the last one? What do you think it's going to do? Up 9. Very good. How many had all 3 of those? Good. Now let's talk about the transformation in the graph. So, I'm just going to do this first one. So if I'm looking at the parent function, I'm going to draw this down here so that I can make a separate. I know that it's a parabola because it's x squared. All right. So the parent function would sit right there in sort of standard position. Again, it's a sketch. It's not perfect. So long as you know that it's a parabola, then it's fine. Okay? Well, I need to slide it up 7. So I'm just going to take this now. And that would be my graph. I don't need to have the parent function on the graph. I don't need to make a table of values. I need for you to show me that you understand that the parent function would just go up 7. That's all I need for the graph. Okay? So you don't have to go crazy over making a table of values and finding all these exact points, that kind of thing. I don't need you to do that. Now, that being said, if you aren't sure where it goes, if you aren't sure what the transformation is, you can make a table of values and graph it and dial it in sort of perfectly and then be able to go, oh, that's what happens to it. That's what happens to the parent function. You can work it that way if you don't see it right away. That's the strategy I recommend. Okay?
Wait, isn't that first one?
So in this case, so for this one, I'd have a v that goes down 3. In this case, I'd have the identity function just would go up 9. Okay? So that's just, you just slide it around. All right, let's talk about right and left. Vertical is pretty straightforward. When it's outside, you just go in the direction of the numbers and the signs. For horizontal slide, it is not as intuitive. Because what happens, first off, the change to the x has to be on an inside, and it will move in the opposite direction that you would think based off the sign. So with the vertical slides, we just used the number, we used the sign, and we went the same direction as the sign. But for a horizontal slide, it works in the opposite way. And I'll show you some examples. Here are your examples. So here's what I mean. These are clearly inside, right? With the quadratic, the squaring, it's inside the parentheses, the -5. With the absolute value, the +2 is inside the absolute value with the x. So because it's inside, that means it's right or left.
Right.
Now, for this first one, intuitively, because it's negative, we would think it goes to the left. But that's why I wrote what I wrote in red. And this theme will recur over the length of this course. So instead of this going left 5, it actually goes right 5. Inside is opposite sign, opposite direction. Ethan, make sure you put your squared in the right place. Okay? So where's the left one going to go? Left 2. Okay, so when you describe it, that's all you have to write for your description. Okay? Now if I were to quickly graph this one, okay, I just know it's the regular absolute value, but it goes to the left 2. That's all you got to do. Okay, so if you can identify the type of transformation and where it goes, then your sketch is just super easy to do. Okay, and again, if you're not comfortable with that, you'd rather make a table of values to be sure that it's in the right place, then do that. Opposite sign. It's positive, you would think right, which means it goes left.
Negative is left.
Will the top one be a quadratic?
The whole left side is always negative.
Okay?
So positive goes.
So that's translations. Let's talk about our next transformation, and that is a flip. It's also known as a reflection. So the reflection is the technical other next transformation. I'm going to teach you 2 reflections. There are more than 2, but in this course we're only going to worry about 2. Okay? And this is where our graphs can start to flip. And so instead of having a upright V, it could be a down-facing V. Or an upright parabola, it could be down-facing parabola. Okay? Here's the first way. Well, actually, wait, before we get to that. I want to talk about the 2 types of flips. We'll have a vertical flip. So it will flip, if this is my graph, it will flip over the x-axis. So if this is their parent function, flip over the x-axis, that's vertical. Obviously, I'm doing a vertical thing here. If it's a horizontal flip, it will flip over the y-axis. Okay, so those are the 2 flips we're talking about. It's either going to flip over the x-axis or it's going to flip over the y-axis. Okay? So, first off, those are our 2 options. It's going to flip over the x or over the y. What will happen, again, this outside idea, if the negative is what makes it flip. If the negative is outside of the x, so using that same concept of outside and inside, then it's going to flip over the x-axis. Because all the y values will change signs. And I'm going to give you 2 examples of outside of with negatives. So here are my 2 examples. Okay. This one is obvious. We've got x inside the absolute value. Negative is outside. So the graph is going to be my upside down V. That's the only thing you need to know about that one. It flips over the x-axis. So the graph for this one is just an upside down V. This one will mess us up sometimes. And there's a reason I wrote this that way. Oftentimes we think this negative is being squared. But it is not. I want you to think about it like there's a gap. to show you that the only thing being squared is the x. The negative is not being squared. So this graph is going to flip over the x-axis, so it's going to be an upside-down parabola, facing downward. If I wanted this negative to be squared, what do you think I would have to do? Yeah, you'd have to put it in parentheses, which would now make it inside instead of outside. Okay? Now, your description for this, when you describe it, you're just going to say, flips over the x-axis. You're going to write those words out. Flips over the x-axis, then you're going to sketch it. Okay, that's your description. All right? Questions on that? Let's talk about inside ones. Inside ones are obvious. Okay? This. The negative's on the inside. Now it flips over the y-axis. And here are my examples. Like I said, it's obvious. The negative is inside the absolute value. The negative is inside the parentheses, squaring it. What's interesting about these two is what kind of graph you get. I'm going to show you here in a second. So I'm just going to draw a set of axes. And let's do this one. Oh, before we do that. This is your description. Flips over the x-axis. I'm gonna sketch this one and show you how this looks. Okay? And I'm gonna do it a specific way. So normally it would be a V. I'm gonna do it in two different, each side in a different color. I'm hoping this will work. We'll see. No, it's not gonna work there. I'm gonna draw it in a different place. Let me draw it in a different place because it wants to connect those as one image, and that's not what I want to do. So I'm going to draw that up here. That's okay. It's not great, but you're going to get the point in a minute. Okay, so now let's put it in sort of parent position. When I flip this over the x-axis, when I flip this over the y-axis, what's going to happen to it? It is going to give me the same thing. Let's watch. Now, this is why I made one side red and one side blue. Okay? So I can flip it with my program, and I get the same thing. So that can happen sometimes. Right. Exactly. So that's why the y, in other words, the y value is not affected by the negative on the inside of this. The y value is not affected by this because it's being squared. So sometimes when you flip over the y-axis, you actually get the same graph. The parent function itself is equal to it as well. So just watch out for that.
Would you get the same graph on the other equation too?
For the parabola?
Yeah.
Yes. Yes. Let's get to the last one. The last one is a dilation. And actually, when we think of the word dilation, we're talking about when you stretch or compress a graph. We use the word to dilate or dilation in everyday life in two really specific ways. What's one of them? When do you know the word dilate? Yeah.
Your eyes.
Your eyes, right? That would be one. When x is multiplied by a number greater than 1, the graph is going to be stretched vertically. Here's the parent function. You don't need to write this down, okay? Eventually you can take a picture, but not yet. So this is the parent function, and I know it's really hard to see, but this is y equals x squared. Okay. Now what I'm going to do is multiply that by a number. Multiply the x squared by a number greater than 1. think it's 5 actually. Okay. So this is, yeah, it is 5. So this is the graph for y equals 5x squared. So as you can tell, it looks like it got pulled up and it got stretched vertically. And so your description will be, and here they are on top of each other. Okay? So there you can see if you take the red one and you pull it straight up, it turns into the blue one. So when you write your description, you're going to say stretched.
Wait, why did you put 5?
I just chose 5.
It doesn't matter.
It just has to be bigger than 1. That's all that matters. Then it would be stretched vertically by a factor, in this case, of 5. If the number was something different than 5, then it would be stretched vertically by a factor of whatever the number is.
So we can pick any number?
No. I chose that for our examples. In your homework, you'll be given a particular equation, particular function, and you'll have to look at it and go, okay, it's stretched vertically by a factor of whatever the number is they put in the problem. Okay? But this is your description. And this is how you can see that this parent function, if I pull it straight up, it just gets kind of skinnier. It gets stretched. Now, one of the things that you might see in your book if you spend time there is they also talk about horizontal stretches and horizontal compressions. So while this is and we're only going to really talk about vertical ones, but if you really got into it, this could also be considered a horizontal compression. Compression, the better way to understand what compression means is smushing. Okay? So if I took the parent function and smushed it together from the sides, that's where I would get a horizontal compression. But for our purposes, I want to just stick with vertical, and then we're always speaking the same language. All right, then the other one is a vertical compression that we're going to look at. When we have a vertical compression, x is multiplied by a number greater than 0 but less than 1, meaning a fraction. A regular fraction. Between 0 and 1. No improper fraction, no mixed number, just a plain old fraction. 2/3, 1/2, 1/4, 3/4, 7/8, whatever. Okay? When you see that fraction in front of the x, then what's going to happen is it's going to smush vertically. And it'll make it kind of push apart. Like we did when I showed you that picture. So let's look at some examples again. So I start off with my parent function, y equals x squared. This one is y equals 1/4 x squared. So again, that's a fraction between 0 and 1. So again, it looks like it got pushed down. And when you push it down, it pops out to the right and to the left. All right, so now I'm going to put them back on top of each other like I did the other one. And so what we would write for our explanation is compressed vertically by a factor of 1/4. Now here's the thing with the graphs of these. Okay, these aren't going to be straight sketches. You're going to have to plug some values in. Okay, in order to figure out where they go. You don't have to plug that many in, but you have to plug enough in. Or if it's a linear, you can use the slope and graph it that way. But ones like this for a vertical compression or a vertical stretch, you're going to have to be more precise than you would have to be with just a flip or just a slide. Those ones are going to take you a little longer to do. Okay? Questions about any of that?